So right now in my life, what's basically going on is Fourier analysis. That is, they are teaching the principles of electrical engineering, and the first thing that they taught us was the Fourier series, and then the Fourier transform, then the DFT, the FFT algorithm. Well, not the FFT algorithm. They just mentioned it's an algorithm for DFT, but we have been using that through computers a lot. And whenever they take the Fourier transform of some function, so say you have a function f of t in the time domain, it's just f of t. Its Fourier transform is given by this integral. So this converts it from a time domain to a frequency domain. And here the frequencies are this omega. So this is the capital omega. And j is the imaginary unit, square root of -1. I know most other fields use iota, that as the square root of -1, but for some reason we use j. But yeah, that's the notation I'll use. So they write the Fourier transform as capital F of j omega, which is weird. I mean, shouldn't just be capital F of omega itself? Why have this j over here? It's like telling us that f of omega would be something else, that if instead of omega you put omega upon j, then that would be f of omega, of course, and that would be like integration from 0 to infinity f of t e power negative omega t, right? So that doesn't look like the Fourier transform. So then why do we have this notation? And what would the integral become if this was, omega upon j instead of omega? Because then it would just be f of omega, right? Which is integration of f of t e power negative omega t. So turns out that that thing in fact has a special name. It's called the Laplace transform of f, the small f, of course. So we use this notation because of the fact that f of s is actually the Laplace transform, right? So the Laplace transform is given by this integration from 0 to infinity f of t e power negative st dt, where s you can think of as a complex frequency. So here omega is a real number, here s would be some complex number, and since you have j omega over here, you have e power negative j omega t, right? Over here, this s thing is actually a complex number, so you can break that as something like a plus bi. So then you would just have e power negative at e power negative jbt. Oh, I said a plus bi, right? It should be a plus bj, of course, stick with the notation. So that means that this is like a more general Fourier transform, kind of like that, right? So not only does actually it give you the frequencies in the imaginary kind of line, so like j omega, right? Here you have j omega, that's an imaginary number. Over here you have any complex number, right? So why do we care about this function? Why do we name it, right? I mean, Fourier transform, we can of course name that because it's useful, but what about this function? Why is this useful? Can we do stuff with it? Well, one of the main uses that it has is solving differential equations of a certain form. So during my J preparation, I came up with a formula for some certain second order differential equation. So suppose you have this differential equation, x double dash minus alpha plus beta x dash plus alpha beta x equal to c, where c is a function of t, and x is also a function of t. So when I say x double dash, I mean the second derivative with respect to time of x. So this has a general solution of this form. So x of t is given by all of this, and I've been using this formula a lot, right? Because to get the solution for some differential equation that comes from the LCR circuit, you will need this formula. To get the solution of the differential equation from damped simple harmonic motion, you will need this formula and whatnot. So yeah, this formula is like pretty important. But the thing is, this is actually not very general. This is only a special case. It's for second order differential equations. What if you had x triple dash involved as well? Then you would be stuck, right? So the way that I got this is basically by multiplying by integrating factors and then factorizing this thing. When I say factorize, I don't mean like literally like you do for polynomials, but kind of in a way, factorizing it, multiplying by e power negative alpha t first, then doing the integration factor stuff, writing it as d upon dt of e power negative alpha t times some other thing, x minus beta stuff, yeah, all that, and then e power negative beta t. You get the thing, right? I've done the derivation quite a lot of time because I used to forget this formula, but yeah. The thing is, this is just a special case. You could have a more general formula. Well, of course, having a formula is harder because you would have to write all of that down, and then remembering that is a very painful thing. But you could have a more general method of solving it with Laplace transform. So before we actually get to the method, first we have to know what Laplace transform really is, like what are its properties and stuff. So the first property is very obvious, that it is linear. So instead of x of t, if you, so first we'll actually define it. So the Laplace transform is given by this thing. So this notation is weird, but that's just the way it is. So it's the Laplace transform of this function x of t, and it's evaluated at the complex frequency. I should stop calling it complex frequency. This could be confusing people, but yeah, it's evaluated at s. So in this curly bracket, what goes is the function, and in the round brackets we put in the argument or the input to the thing that comes out of the Laplace transform, right? The actual function, yeah, whatever, figure it out. Yeah, so we'll sometimes not write this parentheses s, right? I'll just skip this part sometimes, and then I'll just write the Laplace transform of this function x of t, and then in this context it will be, since we are going from time domain to frequency domain, it will be evaluated at some s, right? That's in this context. So it's defined like this. It's by definition the integration from 0 to infinity of x of t e power negative st dt. So s has to be a positive number, otherwise of course this thing kind of explodes. So as t approaches infinity, if this is a negative number, then negative st is a positive thing approaching infinity, so e power that is also infinity. And then if x is finite, which most probably it will be, then yeah, this is useless. So it has to be e power negative st. Awesome. Okay, one important fact about this is that it's linear. So if instead of x of t you had x1 of t plus x2 of t, you could basically write the Laplace transform of x1 of t plus x2 of t as the Laplace transform of x1 of t plus the Laplace transform of x2 of t, right? That's pretty obvious from the definition itself. Okay. Now this has this nice property that the Laplace transform of the first derivative of x, that actually is this thing. It's just s times the Laplace transform of x minus x evaluated at 0. So yeah, just read through all of this. I don't want to be explaining it. It's just a lot of maths really. So if this was not there, if this minus x0 was not there, it would be like really good. So then you just have the Laplace transform of the derivative being equal to s times the Laplace transform of x itself. But this is there, and this is actually important. You can't just ignore it. Sometimes people just ignore it, like they say okay, x of 0 equal to 0, and then this works. But no, that's not how it's gonna be. So for example, if x was sinusoidal, right, if x was like sine of t, then of course x of 0 is 0, so you could ignore that. But when you would take Laplace transform of x double dash, then you won't be able to just say it's like s squared times L of x. No, that's not correct, because the first derivative would be cosine, and then that evaluated at 0, that's 1. So yeah, you can't just ignore these extra things. Of course, using this thing, using this kind of formula recursively, you'll get this formula. So this is the Laplace transform of the nth derivative of x, which is given by this thing. So the s power n Laplace transform of x thing minus all of the extra stuff. So for example, for the second derivative, you just have Laplace transform of x double dash is equal to s squared Lx minus s x naught plus x dash naught. So this is the first derivative evaluated at 0. Okay, that's awesome. You can of course figure out for x triple dash and whatever using this formula. I won't be doing that. Okay, next let's go to the thing called inverse Laplace transform. So of course we can go from time domain to frequency domain, and in Fourier transform you could do the opposite as well, right? You could go from the frequency domain to the time domain by basically integrating. Can we integrate and go to the time domain? Well, we can, but I don't want to be using that. Really, that's the whole thing. I just don't want to be using that integral at all, because like that's a complex integral. And yeah, granted, the integral goes in a straight line, but let's not bring all of that into this. Let's go by the traditional way. So traditionally, the way that inverse of a Laplace transform is calculated is basically the way that integrals are calculated. You have to know your derivatives, and then you can guess what the function should be so that its derivative is some other function, right? So the same thing goes over here. If your Laplace transform is known, then you just have to guess some function whose Laplace transform is the known function, right? So how do we know that this is actually unique? Well, there is a theorem that says it's unique, but I don't want to be proving that. And frankly, I have not actually searched for its proof because, yeah, kind of lazy, and because I'm in the middle of semester. But yeah, so it's unique, and that means you just have to guess this function, and once you have this function, you have it. Okay, so let's try to figure out the inverse Laplace transform of something very simple. So the inverse Laplace of a constant function. So you just have f of t equal to k for all t. Then what's its inverse? So that I'll just tell you is k times the Dirac delta function in one dimension of t. So yeah, it got pretty complicated pretty fast, didn't it? So what is this delta function, by the way? The delta function can be thought of as the limit of a sequence of functions. So consider these kind of functions: 1 minus signum of t times t minus r upon r. Try to graph this and you will see why I'm using something like that. So the area under the curve of this function without the r approaching 0 plus of this function, right, for some finite r, that would be 1, of course. Now as r approaches 0, well, this is basically a rectangle, all right? This thing, its graph is going to be a rectangle. So that rectangle's width starts to decrease, which is r, of course. R is the width, and its height, which is 1 upon r, that increases, but the area remains constant. It's just 1, right? So we use this Dirac delta function in multivariable calculus, and yeah, I was reading a book on that, and because of this I just know about it. Okay, so this is in the first dimension. There are 3D stuff, we won't be talking about that. Okay, so this is like having a nice property that if you integrate from, okay, you integrate over some interval that contains 0, and you integrate like some function times the Dirac delta function, then you basically extract the value of that some function at 0. So for example, if you have this integration from 0 to infinity, f of t and the Dirac delta function of t dt, then that would just be f of 0, because everywhere else the Dirac delta function is 0, so just doing 0 times f of t, that's 0. So that does not contribute anything. The only contribution comes from the from this interval from 0 to r, and of course r approaches 0, so it's like exactly at 0 but not quite. And yeah, just know that that actually gives you f of 0, right? I don't want to be proving all that really. There are formal proofs for it, but right now let's not go into that. Okay, so now let's verify that this actually is correct. So is the inverse Laplace transform of some function, some constant function k, just k times delta t. Let's verify that. So if we can just prove that this guy's Laplace transform is k, then we are done basically, because it's unique, right? The inverse is unique. So let's go for it. Integration from 0 to infinity of this function k delta t. I should be really just say del t. Yeah, that's what I will say. K del t e power negative st dt, right? This will, as I said, it just extracts the value at 0. So there's also like some things that might not be very easy to notice. The thing is, it's exactly at 0, like the interval starts at 0. So what if you are not taking the yeah, so like what if 0 is not included, right? That could be a problem. So for example, let's draw it. So if the Dirac delta function was actually defined like this, so it's the limit as r approaches 0, like this thing is r, right? This width is r. Here's 0, and the Dirac delta function was the limit as r approaches 0 of functions that look like this. I don't know what kind of function looks like that, but yeah, it's as r approaches 0, this thing goes up, the area still remains 1. And then if you were using this kind of Dirac delta function, then you only have this area, right? Only this area, and that times f of 0. So yeah, the area would not be 1. So like the integration of f of t, del of t from 0 to some other value a, this in that case would not be equal to f of 0, because this area that you have is not 1. So only when this is actually 1 can you write f of 0 times 1. Over here you would have to write f of 0 times whatever fraction of area, or okay, whatever area this actually is, let's just call that a. So if this is area a, this area is of course 1 minus a. So you will have to write it like this, f of 0 times a. And f of 0 is kind of constant over here, right? In this range, it varies a little bit, but mostly it's constant. Right. And that's why the kind of Dirac delta function that we are using is this, so that you know everything lies to the right of 0, and so that we get f of 0 times 1. Okay, let's get back on track. Yeah, so now let's evaluate this integral. This will just be extracting the value of this remaining part at 0. So this will just be k e power negative s 0, which is k. So yeah, its Laplace transform is k. So that means the inverse of this constant function is k times delta t, del t, whatever. Okay, let's figure out the inverse Laplace of this kind of a function. So it's the Laplace transform of something else, Laplace transform of f of t, and that divided by s minus alpha, right? So this thing is a function of s, and you want the inverse Laplace transform of this to get a function of t, x of t, right? So if x of t is equal to this thing, then you can solve this equation, kind of, right? So what you would do is apply the Laplace transform on both sides, get this integral, right? Because Laplace transform is basically this integral. Then multiply by s minus alpha, because s is a constant with respect to t. So inside of this you can actually put this inside of integration. But before that, I just want to move this minus alpha, this integral, to the right hand side. So after doing that, I can put everything inside the integrals, and you get this equation. Then you solve this by integration by parts. When I say solve, I mean just modify, right? You modify this by integration by parts. And here's another important thing, that s is bigger than 0. That's why when you plug in infinity, this thing will actually be 0, right? And that's why you can write it like this, x of 0, negative is positive, x of 0 plus l x dash equal to l f plus alpha x. Notice that this thing was just the Laplace transform of f plus alpha x. Similarly, this was the Laplace transform of x dash. Okay, but we just know that this thing can actually be written as the Laplace transform of its inverse Laplace transform, which happens to be x naught, x evaluated at 0. I'll call it x naught del of t, right? Yeah, so writing it like that, and using the fact that Laplace transform is linear, you can write this equation, and then just apply the inverse Laplace transform on both sides, and you get this equation. And then solve this first order differential equation. You know how to do that. And so what you'll basically get is x of t is equal to e power alpha t integration from 0 to t f of t e power negative alpha t. Of course, you have to use the fact that del of t at 0 will be yeah, so like at 0, whatever value of the other function you have, you'll be extracting that using the del of t. So somewhere you actually are integrating, I guess. Are we? Let me just see. So you write it as like, okay, d by dt of, oh, so first of all you move this to that side, okay, then you multiply, and you of course move that to this side, then you multiply by the integrating factor, and then you integrate. So in this integration you have this del of t, and in the next integration you don't have it. The reason is because I basically evaluated this part, negative x naught del t e power negative alpha t, right? I broke the integral, I evaluated that part because that was easy to evaluate. That turns out to be negative x naught, right? And from here as well, you get this negative x naught, it cancels, and you get this thing, xt equal to e power alpha t integration from 0 to t f of t e power negative alpha t. Awesome. And xt was, of course, the inverse Laplace transform of this function. So what we basically get is the inverse Laplace transform of this function is equal to all of this, right? Or if you want, you can replace this L of f by capital F of s, right? So then you just have L inverse capital F of s upon s minus alpha t, is a function of time, of course, is equal to e power alpha t integration from 0 to infinity. Now, instead of small f of t, you will have to write the inverse Laplace transform of f, because you replaced this thing by this, right? Okay. And everything else remains the same. So that's awesome. Now we know how to get the inverse Laplace transform of functions of this type, right? Provided that we actually know what's the inverse Laplace transform of this function. From now, I'm just going to call it as L inverse and L transform, because it's a mouthful to call Laplace transform, inverse Laplace transform. Alright, so L inverse of 1 upon s minus alpha, for example, would just be e power alpha t integration from 0 to t. Now, you have 1 over here. Now, what is L inverse of 1? 1 is a constant, and we know how to get the inverse Laplace of constants. It's just the constant times del t. Constant is 1, it's del t. E power negative alpha t dt. Awesome. And we know how to evaluate this integral because you have this del function here. So this is just e power alpha t, because at 0 this thing just is 1. So yeah, power alpha t. So the inverse Laplace transform of 1 upon s minus alpha, now we know how to get that. Awesome. And now finally we are ready to derive our equation, this equation, using Laplace transform. And this is just an example of a more general method where you would be having third order differential equations and all kinds of stuff. So first you have this differential equation, we apply the Laplace transform on both sides, and we use the properties, linearity and the fact that L applied on x double dash is equal to that thing that I showed you, all of that just substituted in, right? And you get this equation, which you can manipulate a bit. You'll get this equation, s square minus alpha plus beta s plus alpha beta lx equal to lc. C is a function of time. Once again, I'm reminding you, it's not a constant. Okay, plus x naught s plus x naught dash, so x dash naught I should say, so at 0, that's the thing, minus alpha plus beta x naught. Awesome. Now you will just divide everything by this thing, which is of course factorizable as s minus alpha, s minus beta, and you get this thing. So it's still looking scary that all we did is just we figured out the Laplace transform of x as another complicated function. Now how do you get x of t? So we of course have to apply the inverse Laplace transform, but before doing that we should probably just do some manipulation with this, and the kind of manipulation I'm talking about is partial fraction decomposition. So if we can decompose this with linear factors in the denominator, then we can use the equations that we just derived, right? This equation and also this equation. So once we do that, you will get it in this kind of form. So it's 1 upon alpha minus beta, and then you have this stuff. I won't be reading all of that. Okay, so it's just partial fraction decomposition, nothing crazy. Now let's apply the inverse Laplace transform, of course, L inverse, yeah. And since Laplace transform is linear, L inverse is also linear. So you can break, so like for one part of it, let's just do it on this little part. So L inverse of all of this is just L inverse of LC upon s minus alpha plus, this is just a constant basically, so x dash naught minus b x naught L inverse 1 upon s minus alpha. And guess what, we know this and that. So we know that this thing is just this and this thing is just that. Awesome. Okay, this thing is that, of course. Yeah, so we figured out the inverse Laplace for this part, same kind of stuff will happen for the other part as well, and then you will combine these to get x of t equal to this stuff. Now there's a lot of extra stuff going on, this constant, you have limits in the integration and all that. Right, I don't like this because it's like very hard to remember. Of course it's hard to remember. How can you remember so much? And you don't actually need to remember this. You can always do this method and get to the result, right? So for higher order differential equations, you will just have to do it. You will have to do this whole derivation, I would say. Yeah, but instead of remembering this, what we can do is we can write this in the indefinite form, and you will just get this. So yeah, think of these constants as being there because of some initial conditions that were given to us. So like x of 0 was given, x dash of 0 was given, or something like that. And similarly, you have this integration because you were integrating with, like, it was definite integration. That's what I was, yeah, that's what I'm saying. uh kind of like that. Okay, I mean, it is in this derivation, it was definite integration, and because of that, you have these limits. That's pretty obvious. But you can also kind of think that because of that, you have these constants. If that was not there, if this was like indefinite integration, then you would have some unknown constants which you would have to include. So constant of integration, and then you will have to figure those out from the extra conditions given to you, right? From the values of x0 and x dash 0 given to you. Nice. So we can of course do this for more, like for higher order differential equations as well. So if you got something like x triple dash minus, I don't know, something like 2x double dash, I don't know, let's actually go with this, something that's very factorizable. So minus 3x double dash, actually plus 3, yeah, then plus 3x dash plus x is equal to 0. If you had something like this, let's not go with 0, yeah, whatever, go with 0. Okay, then first what we'll do, and of course these are function of time, you would apply the Laplace transform. You would have the Laplace transform of x triple dash, that will just be s cube Laplace of x minus, so first you have s squared x of 0, then you have plus s x dash of 0 plus, well, there's no s, and then you just got x double dash of 0. Okay, then you got Laplace transform of this thing, so it's just plus 3 stuff, it's like plus 3s squared lx minus 3 times all of this s x, wait, yeah, right, lx, so s x0 plus x dash 0. Okay, then the first order. Okay, so plus 3s lx minus 3, am I going correct? I think I am. So x of 0, and then finally this thing, so just plus lx, and that's equal to 0. Of course the Laplace transform, wait, no, is that a thing? Yeah, okay, the Laplace transform of 0 is 0 because, as we said, it's just k times del t. In this case, k is 0 itself, so yeah, it's just 0. Okay, that's awesome. So we'll have all of this, we can write it as lx, and then this polynomial s cubed plus, okay, all that stuff, which we know is just s plus 1 cubed. Awesome. And that is equal to, all of this goes to the right hand side. So yeah, what's all of that going to be? First you got s squared x naught, it's not s squared, then the s term is having x dash naught, and then this stuff, so plus s times x dash naught minus 3, it's not minus, actually plus 3, because this is, yeah, that goes on the right hand side, plus 3x naught. Okay, then the constant terms, so plus x, okay, plus 3x naught dash, plus 3x naught, right, awesome. So these are just kind of like constants, right? Okay, and then if you like knew what these were, right, what are the values of these things, I'm just gonna put in values by myself. So let's just say that x naught equal to 1, x naught dash is equal to 0 something, x naught double dash equal to 1 as well. So then this would be the same thing as this equation. So x naught is 1, got s squared over there, then plus s of all of that stuff. So that's 0, then this thing is 1, so just plus 3s, then you have this thing, so it's 1, yeah, plus 0 plus 3, so plus 4, right? That, does that look correct? I think it does. Okay. This is still weird. Is this correct or not? X naught dash was 0, then 3 x naught is 1, so it's like 3s. Looks about right. Yeah, looks correct to me. Okay, so you got something like that. Awesome. Now what? So like you just got Lx is equal to, so you will have to divide this by s plus 1 squared and then do partial fraction decomposition, which is okay. This is kind of harder. Oh, it should be cube over here, of course. We can't just factor something like s plus 1 from here, that's a problem. Well, we can do this, we can do like s plus 1 squared, so you got 2s plus 1 out, so it's just now plus s plus 3, right, which is just s plus 1 squared plus s plus 1 plus 2, and then just have this thing, all of that upon s plus 1 cubed. So that would just be 1 upon s plus 1, and then plus 1 upon s plus 1 squared plus 2 upon s plus 1 cube. You can do stuff like that, of course. And now the thing is, you got the Laplace of x, Laplace transform of x. You want to apply the L inverse on both sides and get x of t. So x is just this, we know how to apply the L inverse on. It's just so like here in this case alpha will be -1, so just e power negative alpha is, well, it's not negative alpha, it's just alpha, so alpha is -1, negative t. Okay, then whatever is the L inverse of this, I honestly do not know how to get that, but yeah, suppose you knew that, then you would be able to do that. See, I told you, I'm just starting to get in touch with all of this. All right, so yeah, if you know how to get that and then you're basically done at that point, right? Okay. There must be some, well, whatever, I'm gonna stop here because I don't want to waste your time anymore. But yeah, I think I proved my point that this is like a much more general and much better method than, making formulae like this and memorizing those. So yeah, I'll stop here. I'll see you guys in the next video. Bye.